Hello and welcome to this recorded e-learning about design techniques that help avoid routing congestion. My name is Frank Nelson. I'm a Xilinx technical trainer and course developer. I'll be your instructor for this module. Our objectives for this module is for you to be able to explain the causes of routing congestion problems and use better design techniques that optimize the routing before a routing congestion problem will ever develop. There is a lot of need for higher bandwidth and increased device utilization in Vertex 6 applications. Many require large amounts of data to be buffered to support the SerDes functionality that is built into the newest FPGAs. This can create routing problems and routing congestion, just like it would in any FPGA. Routing congestion can impact your runtime, but more importantly, your ability to meet your system timing needs. Now, not every device or design will create routing congestion. It will simply vary by the device utilization and the purpose of the application you're building. But it is important to use these design techniques, which will greatly improve your chances of avoiding a routing congestion problem. You should also keep in mind that it is not just the fact that you use control signals in your design, but if you build them efficiently, that is more important. Routing congestion can sometimes be detected by the implementation tools, but sometimes it's not. In the case when it is not, the design tools will fail to route with no warnings in PAR, and it won't detail any specific nets that could be routed. Likewise, you'll also note in this case we have a PAR warning. This sometimes occurs. In this case, the router has detected very dense congested design. In this case, the tools are smart enough to find that there's an issue with the routing solution. Likewise, another symptom of routing congestion is a series of intermediate status stages reported by PAR, and in this case you see a large number of unrouted nets each time, and of course a lengthy implementation time. And as the tools keep trying, you'll note the implementation time does not get faster, and that number of unrouted nets still stays very large. The reason that managing secondary control signals is so important is because they share the general interconnect, which is where your data signals are routed. If your data signals cannot be routed to meet your timing because there are not enough available routing resources to meet timing, then your performance will be impacted. Having more routing resources available means the tools will then have a better chance to meet your timing needs. Use of the global reset net saves general interconnect by allowing you to reset all synchronous elements in your FPGA automatically. Now, the GSR input is an active high global set reset network that is active at the end of configuration by default. So this is a normal part of the configuration process. It configures your device, and then the GSR is activated to set and reset everything in the FPGA. This is routed on a dedicated routing resource, which will save you general interconnect. It can also be used to restore the initial state of the flip-flops in your FPGA at any time, even though this is not recommended. In this case, the routing delay associated with the GSR is rather slow, and it's not characterized. So using this to reset at any time is not recommended for that reason. Now, this is connected to all synchronous elements through a wired OR gate, and this allows a local reset to also drive your synchronous elements in the FPGA and not just reset with the GSR. So both is supported. Some designs can get away without any resets, but many designs will need some resets. Very few designs require resets on all the registers in the FPGA, but most designers want to use a global reset after initialization, and that's what the GSR should be used for. Most ASIC emulation also requires a described reset on every register. To do this, again, we recommend using the GSR. This will save you from routing initial global reset throughout your FPGA and save general interconnect. But again, keep in mind, the routing of the GSR is slow, so usually 3 clock cycles is required for reset after configuration, which is required during the configuration process anyway. So use after configuration is not recommended. Initialization of flip-flops in an FPGA is important for behavioral simulation. In this example, we have behaviorally coded to reset in our HDL. This will allow the simulation to show clearly what condition each flip-flop is in after power up. Synthesis tools will react on this HDL code. Most people assume that this is unsynthesizable code, but it will in effect the initialization value of the registers because that is tied to the register's primitive chosen by the Xilinx Unified Library. Now, the HDL code in this example will reset to a 0 when the GSR is released after configuration. This way, you can have a known value in your chip each time you configure the FPGA. This code will also simulate to a 0 for startup during a functional simulation. If you do not code this, then you will have on your counter, then you will have X's counting +1, and all you will see during simulation is an X counter. But if you code in this way, it will start with a known value, in this case 0. So this is mandatory if you're designed without a reset on the circuit. Now, inferring an initial value only works for data types of standard logic, bit vector, bit, but does not work for integer types. And note that this inference is currently not supported for Spartan 6 devices, but will be. One of the most common misuses of the clocking resource is instantiating components that already have DCMs, PLLs, and global buffers, that is BuffGs, already instantiated as part of their netlist. So always evaluate your use of the clocking resources, particularly for instantiating lower-level netlists, to make sure that you completely design out all the unnecessary or duplicate resources. You should also evaluate the ability of each DCM and PLL to generate additional clock signals that your application may need from the same source. Now this will save you power and global routing resources, which could be used to distribute your secondary control signals, which will save general routing resources and give the tools a better chance to meet your timing and to completely place and route your design. To gate entire clock domains for power reduction, you can use the clock-enabled global buffer resource, the BuffG clock enable, or even the BuffH clock enable. Now, these are for applications that only pause the clock on small areas of the design. Use the clock enable pin of the FPGA register for anything else that is more local than that. Now, in this case, if you have a high fan-out clock enable signal, when you route and connect these to the BuffG clock enable and the BuffH CE, this will save routing that clock enable on general interconnect because it will be connected directly to the buffer, which is directly connected to the clock source. In summary, designs with a high number of control signals or high fan-out nets can make routing your design more difficult. Pulling buried DCMs or PLLs up to the top level and removing any duplicate functionality for your clocking resources will save you power and save you general interconnect, as well as save you global routing resources. You should also use the GSR on PowerUp to reset your circuit into a known state. And to define that known state, you have to code in your HDL the appropriate HDL code for behavioral simulation to start up at a 0. Now, the GSR is used after configuration every time. That's the standard part of the configuration process, so it's already being executed. So it's probably a good idea to take advantage of it and save you from routing an additional global reset net throughout the FPGA. This would actually, in effect, use general interconnect and prevent the tools perhaps from routing your design to completion or meeting your timing objectives. So, also keep in mind, don't use the GSR to reset the circuit during normal operation. This is not recommended, even though it's still supported. And build your HDL code to properly infer an initialization value so you come up in a known state. Also, use the built-in clock enable features, the BuffH CE and the BuffG CE, so that you can save routing a secondary clock enable on general interconnect. Well, there are lots of places to learn more about good design techniques for FPGAs, and they all start at support.xilinx.com. So we want to point you to these resources to learn more about Plan Ahead User Guide, Floor Planning Methodology Guide for within Plan Ahead, and also we want to emphasize that, particularly for this REL, retargeting guidelines for Vertex 5 FPGAs will clarify more HDL coding techniques that you should consider. And if you're also wanting to use a Smart Explorer and a chance to remove your routing congestion problem, we'll talk about that as part of another REL, but that information is provided as well in the Command Line Tool User Guide. If you would like to see what other courses we offer or what other free RELs are available to you, you can go to the Xilinx Education link you see here. In particular, we emphasize and encourage our customers to go to the Designing with Spartan 6 and Vertex 6 device families to learn more about those silicon features and how they can be helpful. Also, though, if you're looking for other RELs on this topic, you can go learn more about the use of area constraints with Plan Ahead. This is a good way to improve your routing congestion. And likewise, what are the benefits of using the Plan Ahead software tool? And finally, how do I resolve routing congestion REL, which we'll discuss numerous ways to resolve routing congestion problems. But whatever you do, please take a second, let us know what you thought of this REL. Just click on the icon at the top of the page and tell us what you thought. Again, my name is Frank Nelson. You've been learning about good design techniques that help you avoid routing congestion. Thank you for listening, and thanks for your business.